Hi, my name is Chaska Moon, and today we're going to talk about the rational root theorem. Here we have an example of a simple polynomial equation. We know that the factors of 8 are 1 and 8 and 2 and 4, and we know that they must equal 6, so we must use 2 and 4. Therefore, x would equal -2 or -4. The rational root theorem was founded by a 17th century philosopher René Descartes. It's based on his Descartes' rule of signs. It applies to a polynomial equation with one variable. The leading coefficient must be divisible by the denominator of the fraction, and the constant term must be divisible by the numerator. We now need to state the equation. We take the leading coefficient q and the constant p, and the theorem states that all factors are products of positive or negative factors of p over the positive or negative factors of q. Here we have an example where q would be 2 and p would be 8. Knowing what p and q are, we now can write all the factors of p, which is 1, 2, 4, and 8, and q, which is 1 and 2. Using q as 1, here are the factors. Using q as 2, here are the factors. We see that some are duplicates. Knowing what p and q are, we now know that our potential factors are positive or negative 1/2, positive or negative 1, positive or negative 2, positive or negative 4, or positive or negative 8. We now use synthetic division to find the answers. Here we take 2 as a factor. We will synthetically divide, filling in all x's that are missing with zeros. You take 2 and take it to the bottom. Then you multiply it by the positive 2 in the box to give you 4. You then add that down, which would give you 4, multiplying that by 2, and so on and so forth. You get a remainder of 32, which shows that positive 2 is not a factor. Here we see the solution with the remainder in the correct mathematical term at the end. Here we see all the possible solutions showing that this equation in fact does not factor. We have covered the rational root theorem, how to synthetically divide correctly, and we have gone over an example of the rational root. Here we have another example where p is 4 and q is 1. We know that the factors of p would be 1, 2, and 4, and the factors of q would be 1, giving us our possible factors being positive or negative 1, positive or negative 2, and positive or negative 4. Here we take -2 as a possible factor. Now we put -2 in the box, and we synthetically divide, bringing down all coefficients, filling in any empty coefficients with 0. We then multiply and add throughout, and we get a remainder of 0, which shows that this is in fact a factor of this equation. Here we have a chart showing all the potential factors, and we see that 1 and -2 are in fact factors of this equation. Here is another example where p is 3 and q is 4. The factors of p would be 1 and 3, and the factors of q would be 1, 2, and 4. Using q as 1, here are the factors. Using q as 2, here are the factors. And using q as 4, here we have the potential values for this equation. positive or negative 1, positive or negative 3, positive or negative 1/2, positive or negative 1/4, positive or negative 3/4, or positive or negative 3/2. Now we use synthetic division to see if negative 1 is a factor of this equation. Now using synthetic division, we see that we have a remainder of 6, which means that this is not a factor of this equation. Here we have a chart listing all the potential factors. We see that 1, 1/2, and negative 3/2 are factors of this equation. In recap, we apply the theorem to define the potential factors using the theorem, the positive or negative factors of P over the positive or negative factors of Q. We then use synthetic division to see if it's a factor. If we get a remainder of 0, it is in fact a factor. Thanks for watching my video on the rational root theorem.